Okay, thank you, Professor Zhu. And I'm Ruobin Dai from Tongji University, and I want to thank Professor He to organize this seminar for us to communicate our recent advancing in our research. And actually, I did this slides in Chinese, and I prepared this slides in Chinese. So, but I noticed that if I speak in Chinese, as I'm the only one to use English, use Chinese in this conference, so I have to speak English but use the slides in Chinese. So I hope you can understand the things I want to introduce. So actually, my presentation is about to understand the micropollutant rejection mechanisms by the polyamide memories by using the data knowledge code-driven machine learning. And my slide has divided into 4 parts, but everyone knows that the first part is about the background. So the first one is that we know that the memory technology actually has been widely applied in water and wastewater treatments, and it has several advantages. But however, there's we know that the topic of this conference is about the micropollutant. So there's a figure that we cooperate with the Professor Tang that we noticed that for NF and RO memories, which are both polyamide memories, they fell in short in removal of the micropollutants. For this problem, and we know that our polyamide memories are designed for the removal of salts from water, but not actually for the removal of micropollutants from water. So, but however, there's the mechanisms underlying the rejection of micropollutants by polyamide memory is quite complex. We know that there's size exclusion and electrostatic repulsion and hydrophilic hydrophobic interaction and other interactions. So that's when we use the conventional models or conventional mathematical models, we cannot distinguish these complex mechanisms. So now we think about the machine learning, and the machine learning has the characteristics of the data-driven, and we don't have to use the control equation. Also can to deal with the nonlinear problem, and the interpretation of the model has been improved recently. So, but for the application of the machine learning in the memory field, the problem is that one is the scarcity of data scarcity, and another one is the heterogeneous problem of the source data. So, I had like to make a comparison like that. If the machine learning is like we driving a car to the destination, and the data is like the fuel of the vehicle. So if you don't have the enough fuel for us, so we cannot get to the destination we want. So what can we do? So we can incorporate the conventional knowledge or the conventional mathematical models into the machine learning to improve our make a sign in the on the road, so we can achieve the destination by using the data knowledge code-driven machine learning. And so in this presentation, I will introduce the combination of the data and the knowledge in 2 ways. The first one is I like to incorporate the mathematical models into the machine learning directly, and the second one I will introduce the works about the causal machine learning. And the first part is that we collected data from the reference we collect about the 2,000 data points from references, and we divided this data set into 3 parts, including the neutral hydrophilic micropollutants, and the second one is the neutral hydrophobic micropollutant, and the third one is about the charged micropollutants. And we incorporate 3 models to transform the original data and to incorporate to combine the data and the knowledge. And the first one is actually the partition coefficient coefficient, the phi that actually was introduced by Professor Tong in his slides, and to introduce the understanding of the size of the micropollutant size and the pore of the membrane. We want to let the machine to run it first, and second one is the charge product that is the product of the zeta potential of the membrane and the molecular charge of the pollutant, so that the machine can understand that if the charge product is positive, that there's a repulsion, electrostatic repulsion between membrane and the pollutant. And the third one is about the log D, that we want the machine to understand that when the dissociation of the micropollutants will also will influence the hydrophobicity of the pollutants. So then when we have when we transform the original data by these three conventional mathematical models, and we then use the XGBoost, a kind of boosting algorithm for the machine learning, and to then this is a result of our prediction. And but actually, this DD model and the DKD model. Then DD is data driven, and DKD is refers to the data knowledge core driven model. And actually, from these results, that we the predictive accuracy of these two models is quite. There's not very large difference between these two models. And actually, we want to say that when we introduce these different parameters like phi and the charge product and other things, it changed the feature importance in this figure. You can see that for example, for the DKD model, the phi plays a more important role than the molecular weight and the pore size of the membrane. It means that the machine thinks that the phi plays a more important role than the size of the micropollutants and the pore size of the membranes in the rejection of the micropollutants. And this slide is quite important, that unlike the R square that shows quite no difference for these two models, but in this part, that for the conventional DD models, it cannot distinguish the effect of the hydrophobic interaction, but our DKD model can know that the hydrophobic micropollutants always have a low rejection in the membrane filtration. And for the DD model, that also cannot well understand the effect of charge product, the effect of the electrostatic repulsion. But when we use the DKD model, it will understand that when the membrane and the proton have the same charge, they will have the electrostatic repulsion, and the rejection will be high. And also we can understand we can divide the membrane to the NF and R membranes. We know, and we will know that the specific. Also, we can quantify the specific mechanisms, including the yellow one is the size exclusion and also the charge effect, etc. And in this figure, we can find that for the R membrane, that the size exclusion plays a more important role than the NF membrane in the rejection of the micropollutant. And also we can study these mechanisms by dividing different micropollutants. That because in this slide we know that we can study this by different membrane types, and also we can divide the pollutants to neutral hydrophilic and neutral hydrophobic and charged micropollutants, and the detailed effect will be can be quantified. Now, then we did some work in our laboratory and to validate the results of our model. And the third part is about our second way to combine the data and knowledge, that is to answer the question of if and then in the rejection of micropollutants by our polyamide membrane. Because we can see in this figure that for our conventional machine learning, that we think that the features xe to xn, like pH, zeta potential, or membrane pore size, we think they have an equal contribution or the equal initial contribution to the rejection to the rejection. However, actually, we know that there's some causal relationships between these things. For example, that for the pH, how the pH affects the rejection. Actually, pH affects the zeta potential of the membrane. Also, it affects the dissociation of the pollutants. So we have to use the causal machine learning to decouple that. We know in this figure that there's for one X, there's a direct effect to the on the rejection, and also there's an indirect effect to another feature, and then there's a mediated effect on the rejection. So when we did the causal machine learning, it's actually when we did it using we will do this one first. That this is the second way we combine the knowledge to and the data. It is that we will draw a figure like this. This is our knowledge. That's because we know how the pH affects the rejection. Actually, there's a way for zeta potential and molecular charge, but we don't know that we cannot quantify each avenue for this. That we don't know that the pH can influence more on the potential and to influence the rejection by rejection, or if this avenue matters. Don't understand that, so this is why we should do the double machine learning or the causal machine learning on it. So in this way, we can see that we can understand the upstream variables, the effects of the upstream variables, and also we can understand the contribution of the downstream avenues. So for example, if for the zeta potential, we can know that the pH and the membrane type can also both of them can influence the zeta potential and to affect the rejection by the membrane. But actually, the membrane type plays a more important role than the pH. And also for the downstream avenue that we can understand is that for the pH, it affects the zeta potential more than the molecular dissociation. So the pH can influence the rejection more through this avenue. Yeah. And then we have an example is that we're using the pH. We can draw a simple one, and this is the quantified contribution for how the pH affects the OMP our micropollutant rejection. And this is a simple illustration of how the pH affects the OMP rejection. That we have found that when the pH can influence the membrane surface charge, and this effect is larger than the pollutant molecular charge. And also there's some side effects, like when the pH affects the charge of the pollutants. The charge of pollutants will also influence because the dissociation will affect the hydrophobicity of the pollutants. And so when we finished our causal machine learning, so we can draw a picture like this. That is the quantified contribution of each parameters or each features to the micropollutant rejection. So from this figure, it can guide our design of the materials to optimize the rejection of the micropollutants by our polyamide membrane. And also, we can do some optimization based on the causal machine learning. But in this figure, actually, we make the pore size constant, and we can change other parameters. Because you know that when we narrow the pore size, we indeed can obtain the high removal of the pollutant, but actually the water parameters will reduce. So we intended to intended to fix the process and to see that if we optimize the charge or the hydrophilicity of the membrane. So what's the limit? What's the upper bound of our material optimization? So you can see that the average rejection of the MP can improve from 61% to 80%. And the final part is about the conclusion. Actually, we know that and we believe that the data knowledge core-driven machine learning is important or key direction for our mathematical model development in our future, and to facilitate our understanding of the rejection mechanisms of ions and micropollutants by polyamide membranes. And also in the future, and we will do some works about that, because recently we know that the large language model is very popular in our daily life and our works. But actually, we want to answer the question is that for the large language model and our conventional models like our boosting method, which one is better, which one is better for us to understand the mechanisms of the rejection by the membrane? So this